Now we are ready to show the actual experiment itself. This setup can be used both for interference as well as diffraction. As it is shown here, now we are showing the interference setup. The only difference between what is being shown here and what is there in the book is that in the book it is along the y-axis and we are putting this along the x-axis. The reason for that is very simple. In this case, it gives us much more distance between the screen and the plate, which gives us the fringe pattern much more clear. But in the case of diffraction, we can even put it vertically up to down. But it doesn't really matter whether we use it horizontal or vertical. So what this has is a plate consisting of a series of double slits with different distance between the slits and a series of diffraction gratings. So these white patches which you are seeing actually contains a number of lines which we cannot see with the naked eye. These are so close to each other and they have different grating constants, which means it is 1 over the number of lines per meter is called the grating constant. So you have different gratings with different grating constants. So we can put the laser beam through the double slits. We get the Young's double slit experiment where we can get the interference, and if we put it on the grating, we get the diffraction grating orders and we can describe that one. So this is a diverging lens so that the beam can be diverged to fill both the slits, and then we are using a green diode laser. So with this, we can see the interference pattern, and the interference pattern has got equally bright fringes, and we measure the distance between the fringes, either dark or bright fringes, and then that gives us our D, and we have the L, which is the distance between the screen and the plate, and then of course we can calculate the wavelength. What you are now seeing is the interference pattern. You can see that there is a patch-like thing in which you can see the bright and dark fringes, which are the interference fringes. As we have described before, the interference fringes are all of equal intensity. But you may be wondering why those fringes are confined to a very small spot. The size of that is a function of the laser properties. For example, the laser, if it has got smaller beam divergence and larger coherence length, then that spot will be bigger. This will be very important when you are taking a hologram. When you are taking a hologram, the size of the hologram depends upon the physical characteristic of the laser. You will also see that on either side of the interference fringes, you have the diffraction orders also, within which you again see the interference fringes. As you remember, we've said before that interference cannot take place without a diffraction, whereas diffraction can be independent without the interference. So what you're seeing is, one more time, is the interference pattern wherein the fringes are all of equal intensity and the number of fringes on the spot correspond to the distance between the slits through which this light is passing. So the Young's double slit experiment, which is what we are showing, will enable us either to calculate the wavelength or to calculate the distance between the slits. Now we will be showing the diffraction pattern. For this experiment, what we have done is we moved that plate from the double slit to the diffraction grating. We can repeat the experiment with number of gratings on the plate. There are number of gratings with different grating constants. So we have put on one of them, and what you will be seeing on the screen is a diffraction pattern. The most distinguishing difference between the interference and diffraction you can see here, you can see only the individual diffraction spots, whereas in the case of interference, we saw these fringes of equal intensity. The second thing you will also notice is that the central order, which is called the zero order, is the brightest, and on either side you see their first order, they are less intensity, and then as you go further down, the intensity becomes still less and less. So therefore, as we said before, the interference and diffraction are two different phenomena, and we should not confuse between them. The third most important thing is the distance between those spots is dependent upon the grating constant. So you can see that the larger the number of lines, you have a different spacing. That is controlled by the equation that m lambda equals to b sine theta. That equation is there in the book, and you can measure the distance between any two orders, same orders on either side, and divided by 2, that gives you the distance between the 1 order and the 0 order. That will be our y, and once again the length is the L is the distance between the plate and the screen, and with the d we already know, we can calculate the wavelength again. So this experiment, the beauty is that both the experimental interference and diffraction can be shown by the same experimental setup.